Hello friends, welcome back to your favorite channel. In the last video we had discussed about fin with finite length and heat dissipation at the tip. Means we are moving from ideal case to the real case, and based on this we had solved some numerical which may helpful to you for your regular as well as in the competitive examination. Friend, in this video, that is heat transfer by conduction part 11, we are going to discuss about fin efficiency and fin effectiveness part. So friend, in this video first we will discuss about what is the necessity to describe these two terms, that is fin efficiency and fin effectiveness. Then we will discuss about fin efficiency and fin effectiveness. We will derive the formula for different type of fin. Then we will discuss about the equations which we will get, and based on that we have to solve some numerical that will again helpful to you in your competitive examination as well as in your regular examination. So friend, we know that the fins or extended surfaces are used to enhance the heat transfer as they increase the total heat transfer area. So when we are going to design the fin or when we are going to install the fin, we have to go for optimum design of the fin, and during this design we have to consider the following factor. That factor include the total cost, manufacturing problems or difficulties, complexity associated with the fins, weight, pressure drop, and space consideration. These are very important criteria which we have to discuss, which we have to consider, which we have to look up, and at the end we have to decide whether we have to install the fin, whether we have to install extended surfaces or not. But friend, we know that when we use the fin, this fin will act as a resistance to the heat transfer, and so one has to decide whether fin should be installed or not. So a parameter that is called fin effectiveness that justifies the use of fin if the value of fin effectiveness is greater than 5. So friend, we are going to discuss about the first parameter, what is called fin effectiveness, and fin effectiveness is the parameter which justifies the use of fin if the fin effectiveness value is greater than 5. So friend, first we will define what is called fin effectiveness. So the fin effectiveness is defined as the ratio of heat transfer rate to that of which would occur from the surface on which fin was attached. Therefore, we can say that epsilon, that is effectiveness of fin, that is a ratio of heat transfer with fin divided by heat transfer without fin, or you can say that is Q with fin divided by Q without fin. So if we will consider the first case, that is fin of infinite length, we can say that heat transfer with fin, that is under root of PHAK into T0 minus TA, and heat transfer without fin, that is convection heat transfer, that is HA into T0 minus TA. So if we'll find out what is the solution, we will get that is under root of PK divided by AH, where P is the perimeter, A is the cross section area of the fin, K that is the thermal conductivity of the material which we are using for the fin, and H is the convection heat transfer coefficient of surrounding fluid. The surrounding fluid may be atmospheric air, it may be a liquid, or it may anything. So based on this equation which we will get for the infinite length fin, that is under root of Pk divided by Ah, we can conclude something, and that we have to discuss. So from the previous equation of fin effectiveness, that is under root of Pk divided by Ah, we can first conclude that if we want to increase the effectiveness of fin, we have to provide the material which is a very good conductor of heat energy. Means we have to use metal, or we have to use the copper or aluminum which is a good conductor of heat. So generally we are preferring aluminium as a best choice because it is cheaper, it has very high corrosion resistance, and it is in lighter in weight compared to copper. So we can observe, particularly in case of two wheelers, that is in a bike, in a Activa, in a scooter, the fins which we are using, they are made up with aluminium or aluminium alloys, as they are lighter in weight, they are cheaper, and they have very high corrosion resistance. So first thing is very much clear to us: if thermal conductivity will increase, effectiveness will increase. Now the second thing which is known to us is, if H value is less, that is if convection heat transfer coefficient value is less, effectiveness will be increased. So if we'll talk about when the fluid is flowing with very high velocity, whether the boiling or condensation is going on, that is the phase transfer is going on, in that case the H value is very high. You can say that value is more than 20,000 watt per meter square Kelvin. So we have to put the fin where the air or gas is available and preferably natural convection is going on. If the forced convection is going on, or if phase change is going on, or if the fluid is flowing with very high velocity, in that case the convection heat transfer coefficient value is very high. So if we want to increase the effectiveness of the fin, we have to put the fin at the place where convection heat transfer coefficient is less and preferably natural convection is observed. Also, we can say that if we want to increase the effectiveness of the fin, the ratio of perimeter to the cross section area must be very high. So if we want to increase this ratio, in that case, instead of using one thick fin, we have to use large number of thin fins. And when we are going to do this exercise, we have to keep the thing in mind that the minimum distance between two fins, that is called pitch, must be adjusted in such a way so that this will not cut the thickness of boundary layer which is developed on the fin surface. So if we are keeping this thing in mind, in that case, instead of using one thick fin, we are using large number of thin fins, and when we are doing this exercise, the ratio of perimeter to the cross section area will be increased, and hence effectiveness of fin is improved. So we can say copper or aluminium thin fin, or you can say slender pin fins, closely spaced, are preferred in most of engineering applications. So friend, I hope it is very much clear to you what is fin effectiveness, what are the different parameters on which fin effectiveness is dependent, and how we can enhance the effectiveness of fin. Now the second important term which we have to discuss is fin efficiency. So fin efficiency is defined as a ratio of actual heat transfer by the fin to the maximum heat that would be transferred if the entire fin surface is maintained at base temperature. So you can say it is a ratio of heat transfer with fin to the maximum heat transfer. So if we'll consider the first case, that is of infinite long fin, we can define efficiency of fin, that is equals to under root of PHAK into bracket T0 minus TA divided by the maximum possible heat transfer, that is H into surface area into T0 minus TA, and that is equals to under root of cross section area into thermal conductivity divided by convection heat transfer into perimeter into square of length fin, or you can say that is equals to 1 upon ml, where m equals to under root of pH divided by ak, that is fin constant. So efficiency of fin for the first case, that is equals to 1 upon ml, where m is a fin constant and l is a length of fin. In the similar way, if we consider the second case, that is the fin with finite length and the tip of the fin is insulated, in that case efficiency of fin, that is ratio of q fin divided by q maximum, that is you can say equals to under root of phak into T0 minus Ta into tan hyperbolic m into L divided by h into PL into T0 minus Ta, and that value is equals to tan hyperbolic ml divided by ml, where m is the fin constant and L is the length of the fin. So for the second case, the efficiency of fin, that is equals to tan hyperbolic ml divided by ml, where the case which we are considering is the fin is of finite length and the tip of the fin is insulated. So friend, these two are the important parameters which will decide whether fin must be installed with the system or not. So based on this, we try to solve some numerical related to the industry for our better conversion of theory to practical knowledge. So friend, we are going to solve the numerical, refer the data. So in the data it is given that an aluminium fin with thermal conductivity 200 watt per meter Kelvin, 2.5 centimeter long and 3.5 millimeter thick protrude from the wall. The base is at 420 degrees Celsius and surrounding air temperature is 30 degrees Celsius. Determine first part, that is the heat dissipated from the fin and fin efficiency for the fin of infinite length and heat loss from the tip is negligible. Take convection heat transfer coefficient H, that is equals to 11 watt per meter square Kelvin. So here friend, in the data aluminium fin is given with the dimension, the base temperature and surrounding air temperature with the convection heat transfer coefficient is given. We have to consider the fin of infinite length long and we have to find out what is heat dissipation, as well as we have to find out what is the efficiency of this fin. So let's try to solve this problem. So friend, in the data it is given length, that is 2.5 centimeter, that is 2.5 into 10 power minus 2 meter. H value, that is 11 watt per meter square Kelvin. Surrounding temperature is 30 degrees Celsius. Base temperature is 420 degrees Celsius. Thickness, that is 3.5 mm, that is 3.5 into 10 power minus 3 meter. Thermal conductivity is 200 watt per meter Kelvin. We have to find out Q and fin efficiency. So for first case, we have to consider the Q value, that is equals to under root of PHAK into T0 minus Ta into tan hyperbolic ml. So where m is a fin constant, the unit is meter inverse, that is 1 upon meter, and the equation is under root of pH divided by ak. So if we will multiply it with L, then you can say m into L, that is equals to L into perimeter, that is twice the width into convection heat transfer coefficient divided by cross section area, that is width into thickness into thermal conductivity. So if we will put all the values, we will get the value of m into L, that is 0.14. So all data are available. You can find the H value, P value, cross section area, thermal conductivity, base temperature, surrounding temperature, everything is given. So when we'll put all the values and we will calculate, we will get the heat dissipation from the fin, that is equals to 213 watt, that is 213 watt. So friend, I hope it is very much clear to you how to find out heat dissipation from the fin. Now the second part is fin efficiency, that is ratio of Q fin divided by Q max, and for this case it is a ratio of 10 hyperbolic ml to ml, so it is, you can say, 99.35%. So I hope it is very much clear to you how to find out heat dissipation and fin efficiency for the given case. Now friend, refer the data for the second problem, that is a steel rod with the thermal conductivity 32 watt per meter Kelvin, 1.2 centimeter diameter and 60 millimeter long with an insulated end is to be used as a spline. It is exposed to the surrounding with the temperature of 60 degrees Celsius and heat transfer coefficient is 55 watt per meter square Kelvin. The temperature at the base of the fin is 95 degrees Celsius. We have to find out fin efficiency, temperature at the edge of the spline and the heat dissipation. So here in the data friend, a steel rod is given with the required dimensions, thermal conductivity, temperatures and heat transfer coefficient value. What we have to find out is, we have to find out fin efficiency, temperature and heat dissipation. So friend, we can see here the first case, the fin efficiency, that is ratio of 10 hyperbolic ml to the ml, where m we know it is a fin constant, that is under root of pH divided by AK, and that value, upon putting the value we will get is 23.93 meter inverse. So when we will put all the values, we will get the fin efficiency, that is 62.18%. That is our first required answer, in which the perimeter value is pi into d, whereas the cross section area, that is pi by 4 d square, where d is the diameter of the steel rod which is used as a fin. So if we want to know what is the temperature at the edge of spline, we have to go for theta by theta 0, that is T minus TA divided by T0 minus TA, that is equals to cos hyperbolic M into L minus X divided by cos hyperbolic ML, where we know that at X equals to L, when we'll put, the equation is reduced to Ti minus Ta divided by T0 minus Ta, that is equals to 1 upon cos hyperbolic M into L. And when we'll put all the values, you can see that is Ti that we have to find out, minus 60 divided by 95 minus 60, that is equals to 1 upon cos hyperbolic. M value is 23.93 and length is 60 mm, that we had convert into meter, that is 0.06 meter. So we'll get the value of Ti, that is equals to 72.66 degrees Celsius. That is our second required answer, that is temperature at the edge of spline. And now the third answer which we have to find out is the heat dissipation part. So for the heat dissipation part, the fin with finite length, we will get the heat dissipation, that is equals to cross section area into thermal conductivity into fin constant into T0 minus Ta, that into 10 hyperbolic M into L. So when we will put all the values here for cross section area, thermal conductivity, base temperature, surrounding temperature, length of the fin and fin constant, we will get Q fin, that is equals to 2.7 watt. That is our third required answer. So friend, I hope it is very much clear to you how to solve such kind of problem, which is, you can say, a real field experience. Now we try to solve one more numerical, that is a copper fin with thermal conductivity 380 watt per meter degree Celsius, 60 centimeter long and 5 millimeter diameter is exposed to air at 20 degrees Celsius. The convective heat transfer coefficient is 20 watt per meter square Kelvin. If the fin base temperature is 150 degrees Celsius, determine the heat transferred and fin efficiency. Assume the tip of the fin is insulated. So friend, again this is a case of fin with finite length and tip of the fin is insulated. Here the copper fin with the dimensions are given, convection heat transfer coefficient, base temperature, surrounding temperature is given. We have to find out what is the heat transfer and what is the efficiency. So friend, like previous numerical, here first part we have to convert all the centimeter and millimeter into meter. So uniformity in the dimension is observed, and we know that first part, that is heat transferred, that is Q, that is equals to A cross section into thermal conductivity into fin constant into base temperature minus surrounding temperature into tan hyperbolic M into L, where m is a fin constant and that value is under root of pH divided by ak, where p is the perimeter, that value is pi d, and cross section area, that is pi by 4 d square. So from that we will get the value of fin constant m, that is equals to 6.49 meter inverse, and when we will put all the values we will get the value of q, that is 6.29 watt, or if you want to find out in terms of joules per hour, we will get the answer heat dissipation, that is 22,644 joules per hour. That is our first required answer. Now the second part which we have to find out, that is fin efficiency, that is a ratio of tan hyperbolic ml to the ml, and ultimately when we put all the values of m and length of the fin, we will get the fin efficiency, that is 25.66%. So friend, in this video we had discussed about two important terms related to fin, that is fin efficiency and fin effectiveness. We had also discussed what is the formula for fin effectiveness for the different cases of fin and how we have to conclude based on the equation which is derived. In the similar way, we had also discussed about fin efficiency part, and at the end we had solved some numerical related to real life application. So friend, if you like this channel, do not forget to subscribe this channel and share this channel among your friends. Have a nice day. Thank you.